So hello, good afternoon, happy new year. This is the first lecture in 2022. And because of this holiday season break, I really needed to reboot my random access memory to remember what I was talking about, to remember what I was going to talk about. And please allow me to begin with drawing for you a table, sort of a roadmap showing where we are, where we were, and where we are going. And the table is as follows. We invested a lot of time and energy to understand a very fundamental and important, and I think fruitful problem of functoriality of the construction of graph algebras. So I take the category of graphs, one or another, and we assign to objects and morphisms in this category graph algebras and algebra homomorphisms. So first step, of course, which was done in the previous semester, was path algebras. Okay. And well, as I said, we are interested in both covariant and contravariant functoriality. So covariant functoriality and contravariant functoriality. Okay. So for path algebras, this was done in the previous semester, and to have covariant functoriality, we could take general path morphisms of graphs, provided that they're injective on vertices. So path morphisms injective on vertices. And we baptize this category IPG. Okay. Now for contravariant functoriality, we needed much stronger assumptions. So first, we needed our morphisms to be really proper graph homomorphisms, and moreover, we wanted them to be proper. So here, in order to have this contravariant functoriality, we assumed that we are talking about proper, so finite to one, graph, not path, but graph homomorphisms. And I forgot, this was POG, I believe. That's how we baptized. Okay. But still, these were not very restrictive assumptions. Real fun started in this semester, when first we looked at what we need in order to get con path algebras. And for covariant factoriality, we had this M condition. I don't know why I called it M. For monotonicity, I don't know. M condition. And anyway, explicitly, I'm still making these random marks. That's a drawback of not lecturing from IMPAN, where I have this super duper tablet. Okay, so M condition says that if you take an edge E and an edge E prime, and if f of E is less or equal than f of E prime, which means that f of E is a subpath of f of E prime, then this implies that E is equal to E prime. So this condition is for edges. We do not assume it for paths. For edges only. And we discussed in detail why it is important not to assume too much. And that's something which I'm going to prove today. Oops, I need to leave space for Levitt. So today I want to prove that this M condition, it really yields a subcategory. Because you see, of course, when you have a category, nobody can stop you from producing conditions on your morphisms and restricting them. But in order to claim that you have subcategory, you have to verify two conditions. First, that identity satisfies your condition. And secondly, that if two morphisms enjoy such a condition, then their composition in your category also enjoys this condition. And that's, of course, not obvious and not guaranteed. Yeah, the idea being that, I don't know, composition of injective maps is injective, composition of continuous maps is continuous, and so on and so forth. So when you have some very simple natural conditions, it's a piece of cake to see that indeed they carve out the subcategory in a category. But for instance, and this is what I'm going to prove for you today, that the M condition does yield a subcategory, that's not an obvious proof. And you can see why it is not obvious, because when you want to iterate it, and when you remember that you have path morphisms of graphs, okay, then all right, E and E prime are of course edges, but f of E and f of E prime are no longer edges. So when I apply another morphism G, I have G of f of E and I have G of f of E prime. But I cannot use this condition directly because f of E is not an edge. And this is assumed for edges only. Okay, so that's why it's a little bit of fun, which I'm going to have today. Now for contravariant factoriality, remember we had this target bijectivity. Which basically says that if I take any edge X and I take its preimage under F, and then I apply to this subset of the set of edges, I apply the end map, the target map TE, okay? Then, as one can easily verify, I land in the preimage of the end of the edge F, of the edge X, okay? And we demand it to be bijective. And this we proved that it yields a subcategory. Just before holidays, okay? Then for path algebras, so you see when I'm saying conpath algebras, I have to take care of the first closed-figure relation, right? That's why I have to put some extra conditions on morphisms so that the first closed-figure relations are satisfied. Now, when I want to upgrade from conpath algebras to Levi path algebras, I also have to take care of the second closed-figure relations. And here in the covariant situation, we had this very complicated regularity condition. Sorry, I have to spell it correctly. Regularity condition. And this is quite complicated. This condition is quite complicated. And I will explain today why I call it fractal-like. And hopefully we'll prove today that it yields a subcategory. I finished the proof more or less 15 minutes before we started this lecture. So Niklas, you'll have to watch me. I hope the proof is correct. I really put a lot of effort to make sure it's rigorous, but this regularity condition is not so tangible. It's difficult to formalize. So please pay attention that I'm not saying anything stupid. As I said, I finished the proof 15 minutes before the lecture, and I hope it's correct. We'll go through it today. So that's the only two things on the menu today, proving these two lemmas. Which we should have done earlier, but I simply completely forgot. I was so rejoiced with proving that indeed under such a condition, I have a nice functoriality in my construction of conpath algebras and Levi path algebras respectively, but I completely forgot to verify whether I did start from a subcategory. Okay, so that was a serious omission, and well, but the psychological reason is very simple. Such conditions are typically, obviously, yielding a subcategory, right? When you have the category of, I don't know, topological spaces and morphisms are all possible, you set theoretical maps and then you restrict to continuous maps, you don't think that it deals with subcategory because it's so obvious that composition of continuous maps is continuous. So this was my mental mistake, but we are going to rectify today. And well, speaking about the wolf, you see the CR condition here, which was needed for contravariant functoriality for Leavitt path algebras. CR, which stands for what? For complemented regularity. CR condition, which basically says that f of not regular vertices is still not regular. In other words, your morphism must not regularize a vertex. Okay, and this is obviously yields a subcategory. So out of these four conditions, that's the only one which is obvious. Well, but before it was obvious. I mean, to have POG out of OG and to have IPG out of PG, that's obvious. I mean, if you're injective on vertices, then composition is injective on vertices. Identity is injective on vertices. If you are proper, then the composition of finite to one is finite to one. It's also obvious. So you know, when you have here these six conditions, if you will, that three are non-obvious and three are obvious. And one we proved before the break, and two are going to prove today. So that's my plan for the lecture. And maybe let me tell you a spoiler that I would like to end the semester with a push out to pullback theorem, if we manage to prove it, that functions in this contravariant realm, because for covariant, that's the end of the story. Basically, we're proving these two lemmas today. The covariant story is closed for a very simple reason that push-outs of algebras, at least to the best of my knowledge, to the best of my understanding, that push-outs of algebras are not really interesting. I cannot see any excitement in push-outs of algebras, okay? But of course, pullbacks of algebras are absolutely fundamental. But in order to turn pushouts into pullbacks, well, you must have a contravariant functor. So it is in this realm of contravariant functoriality that we are going to see whether having an appropriate pushout diagram in the category of graphs will have a pullback diagram of Leavitt path algebras. But if you remember already from the previous semester that even for path algebras, this adds a lot of additional restrictions. So one thing is to have a functor, but another thing is to make sure that this functor turns pushouts to pullbacks. And we already proved some substantial theorems. I think that it was the theorem of the previous semester, this pushout to pullback theorem for path algebras. There are many subtle and maybe not completely expected conditions that pop out. And they pop out already at the level of path algebras. So now what I would like to see is what pops out for Kohn path algebras and Leavitt path algebras. Of course, at this stage, one should also complain, well, that's just algebra and all the time algebra. Where is the promised land of functional analysis and sister algebras and K-theory? Well, when it comes to sister algebras, I don't think that there is much gain. No, let me do it this way. Of course, there is an enormous gain to go to functional analysis, but I'm trying to say that from our considerations, I don't think that we change much going from Leavitt path algebras to graph sister algebras. And the reason is the following. The reason is that graph sister algebras are defined as universal sister algebras of these algebras. So they behave very much the same way as the algebras which they envelope, okay? It's sort of like if you know the theory of compact quantum groups or classical compact groups, you have this Peter Weil Hopf algebra. And as long as your group is compact, quantum or not, almost all information that you have about your group is in the Hopf algebra, the canonical given Hopf algebra for your compact house of topological group or Voronovich's compact quantum. Okay. Of course, there are many subtleties which are related strictly to analysis, which are invisible at the level of Hopf algebras, but many things are done at the level of Hopf algebra. So the same is here. The relationship between Leavitt path algebras and graph system algebras is very much like the relationship between cosine-simple Hopf algebras and compact quantum groups. So alas, there is no way we can do it during the lecture this semester. But in the recitation classes, and we have plenty of time in the recitation classes, I will try already do some more K-theory of sister algebras, and then show you how it works for graph sister algebras, time permitting. So this will be at sort of a recitation class spot. I will not be able to fit it into the lecture, but I repeat, from the point of view of what we're discussing here, what is new, the graph system algebras do not change much of the picture. I mean, I might be a bit wrong, because in order to prove this push out to pullback theorem, you need to understand the ideal structure. And to understand the ideal structure of your morphisms between graph algebras, well, it might make a difference whether you talk sister algebras or Leavitt path algebras. There are many mirror theorems, but basically one mimics another. So that's why I'm saying that probably not much has changed. My experience tells me that really not much has changed. You have basically the same conditions, but you use somebody else's big theorems in order to justify your conclusions. But we will see. I hope we will manage to prove push out the pullback theorem for Leavitt path algebras, which subsequently can be extended to graph sister algebras. Okay, so if there are no questions concerning my grand picture, my big picture, let's go into proving these two lemmas. Any questions thus far? No? Okay, so let's go on. As promised, we're going to prove the following lemma. In the notes, it's lemma 243. Restricting morphisms in the category IPG so path homomorphisms of graphs that are injected on vertices to the morphisms satisfying. I have a warning message. Your internet connection is unstable. Oh, I hope it's just a joke. To the morphisms satisfying the M condition let me remind you again, says that f of E less or equal to f of E prime implies that E is equal to E prime, but only when restricted to their sets of edges. So restricting morphism in the category IPG to a morphism satisfying this implication when restricted to a set of edges yields a subcategory of IPG. And I think that this is the most fun lemma out of these three. Proof. For starters, the condition is obviously satisfied for f being identical, right? Because if E equals E prime, then it obviously implies that E equals E prime. Nobody protests, I hope. Now, assume now that both morphisms F and G satisfy the condition. I have F from E to F and G from F to G. Satisfy the condition, both of them. Okay, so we satisfy the condition, and well, let's get a hypothesis of this implication, the assumption. Satisfy the condition, and let us assume that G of F of E less or equal to F is less or equal than G of F of E prime. Okay, so this is our assumption. One, I mean, we have three assumptions. F satisfies the M condition. That's my M condition. G satisfies my M condition. And the third assumption is that GFE is less or equal than GFE prime. Okay. And now what we want to conclude is that E is equal to E prime. When we succeed, we are home and dry. Okay, so let's consider some cases. I'm afraid there is no other way. So remember from our example for this situation, we are indeed injective on edges, but it doesn't mean that we cannot map an edge to a vertex. So f of e can be a vertex, and we just have to consider such a situation. Okay, so first case, so to say, if f of e is a vertex, what happens then? Well, of course, then also G of f of e is a vertex. Remember, even in the wildest morphisms in any category of graphs, the image of a vertex is a vertex. So a vertex is equal to its beginning, so SG of G of f of e. When I consider, a vertex is a path, and I take the starting point of this path is just this vertex itself, right? But now I use the properties of these being path morphisms of graphs. So I have this commutation between morphism and source map. So first, this is equal to G of SF of FE, and now it has a little bit more sense because FE, no, sorry, FE is still a vertex. In fact, maybe I could have started from here. I don't know. Maybe it's a little bit redundant. Anyway, that's what I need. Let's see. Okay, and sorry. I skipped something here. A little prime, which changes everything. So sorry, it wasn't so tautological as I wrote it. I want to put here a prime, because you see, if you look at this assumption, G of f of e is less or equal than G of f e prime. well, when G of f of E is a vertex, and it is a subpath of a path, that it means that it's the beginning of this path. Okay, so this is why I wrote it. So it wasn't that tautological. Okay, and now we take this commutation. So here we have G of SF of E prime, and I believe I need one more parenthesis. And what's next? Well, now we use vertex injectivity of G. Okay. I really hate these spurious marks, which are made by my hand. So hence Fe, my vertex Fe, is equal to SF of f of E prime. Well, as I said, by the vertex injectivity of G. But consequently, we know that Fe is a subpath of f of E prime, right? Consequently, Fe is less or equal than f of E prime, which implies what we want. Okay. All right. Now this question is not completely symmetric, so we have to consider it, but it's very similar. So matching the same way. And it's not symmetric because this is an inequality. It has direction. Matching the same way. If now f of E prime is a vertex, then what happens? Well, then also G of f of E is a vertex. And let me explain why. You see, now I have to bear in mind our standing assumption. If f of E prime is a vertex, obviously G of f of E prime is a vertex. But if you have a path which is a subpath of a vertex, sorry guys, but it has to be a vertex. There are no other subpaths of a path which is a vertex. Okay, so this is the reasoning I'm doing. So now I know that G of f of E is a vertex. So we can write the following. I take my vertex G of, I mean, this inequality turns into equality when the right hand side is a vertex, when the left hand side is a vertex, which is equal to the right hand side. Okay, so I'm just having equality of vertices. So G of f of E is equal to G of f of E prime. Okay. No, I wanted in the other way. I take G of f of E prime, and it's equal to G of f of E. And now we do the usual stuff. I mean, remember, this is a vertex, okay? And the vertex is the beginning of itself, which is a path. So now I'm using this argument. So it's S of G of f of E. Okay. But this is the same. I can now commute it all the way. No, do I need it all the way? No, I just commute it by one step. So this is G of S f of f of E. Okay. So hence, as before, we have that f of e prime this time is equal to sf of f of e by the vertex injectivity of G. Okay. But now, of course, I can say that f of e prime is less than equal than f of e, so is equal to e prime. So let me write it down. Consequently, f of e prime is less than equal than f of e, right? Because f of e prime is the starting vertex of f of e, so it is a subpath. Whence e prime equals to e as me. Okay, so we have two easy cases done with, and I had to do it like this because you cannot exclude it. This is absolutely a possible situation, and now I simply want to assume that both f of e and f of e prime are positive length paths. So I can write them in terms of composition of x. Okay, so that's the next step. So assume next that f e, well, this is some path which is e1 dot 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 em, and f e prime, well, it's e1 prime dot 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 en prime. I mean, m and n don't have to be equal, right? Where by assumption, this is important, all these guys e1 to em and e1 prime till en prime are edges. This is important. Well, then, because of our assumption that G satisfies the M condition, I apply G to these paths. And by our standing assumption, we have that that G of E1, G of E2, dot dot dot, G of EM must be less or equal to G of E1 prime. Let me skip E prime 2 up to G E prime N. Okay, that's from our standing assumption. This is just notation, and using this notation, I rewrite my standing assumption in such a way. Of course, you can see where I'm driving at. I cannot use the M condition for G if I don't talk edges. That's why I have to write these paths, which are the images of E and E prime under F. I have to write them as composition of edges. Okay, but look what happens here. In such a situation, you obviously have that either G of E1 is a subpath of G of E1 prime or the other way around, okay? So I can write that this inequality implies that G of E1 is less or equal than G of E1 prime, or you just don't know, G of E1 prime is a subpath of G of E1. Is it clear to you guys? Because you see, when I have this left-hand side path as a subpath of the right-hand side, then obviously G of E1 is a subpath of a thing which is on the left. So, but whether it is longer than G of E1 prime or shorter, we don't know. If it's shorter, then we have a first inequality. If it's longer, then you have a second inequality. Okay, but one of these inequalities must hold true. Okay. But now having, it suffices that we have one of these inequalities, and we can immediately conclude, because now I can apply the M condition of G, that E1 prime is equal to E1. And that's a good start. But now if E1 prime is equal to E1, then obviously G of E1 is equal to G of E1 prime. So when I look at these two paths, they have identical beginnings. So I can truncate them. So if this inclusion happens, well, it also happens after cutting off the beginning. Okay. So now it follows that G of E2 dot G EM is less than equal to G of E2 prime dot G2E prime N. Okay. And as usual, you can guess, we can iterate this argument to conclude that EI is equal to EI prime for any I that range from 1 to the minimum of these two numbers M and N. Right? Because one of these numbers is bigger or equal than the other one. Okay. And of course, at a certain moment, when you iterate this argument, we'll run out of edges in one of your paths, and this will stop you. Okay, so this is why I can go only as far as the smallest of these two numbers. Okay. But once you do it, you regardless of which number it is, you'll either have that f of e is a subpath of f of e prime. This is when m is less than equal than n, because you have your path on the left hand side is shorter than your path on your right hand side, or you will run out on the right. So in each case, you will always have the first part of the other path is the path from the other side. Okay, so let me just summarize it. Therefore, f of e is less than equal than f of e prime. So this is the case when m is less than equal than n, or f of e prime is a subpath in f of e. And that's the case when m is greater than equal. Okay. Just look at what's written here. Okay. This is E1 to EM, and this is E1 prime to EN prime. So either FE is a subpath of f of E prime, then when M is less than equal than N, or the other way around. Well, but this is what we want. Okay, so summarizing, and again I have to remove a spurious mark. Summarizing, we have shown that. Yeah, okay, sorry, I forgot to write, yes, so E equals E prime. So summarizing, we have shown if you suppose that, and here I see a typo in my notes. Yes, I have to correct it. is decomposed with F. E is less than equal, and decomposed with F prime, and then it implies that it's equal to. Okay. So M, the M condition determines a subcategory. Because composition of M morphisms is an M morphism. Okay, that's the end of the proof. So I hope you agree that it wasn't completely trivial. That's something that you have to explain. There are no special bells and whistles here, no fancy tricks or technology. It's elementary, but it's not obvious. I mean, it took me, what, 10, 15 minutes to show you the proof, okay? But now we are really happy because we know that we have a subcategory. And the second lemma, which I want to prove today before finishing today's lecture, which, as I told you, is a bit shorter today. The second lemma concerns the regularity condition, and it is less pleasant. It is less pleasant, so please indulge me and help me. I finished this proof, as I said, 15 minutes before the class. So please pay special attention to make sure that there are no mistakes. And it's not the problem that this is such a horribly difficult thing to compute. No, the thing is that it's not so tangible, that somehow formalizing this condition is not so obvious. It's not so obvious how to phrase it. And let me warn you, you have to be very careful. I just refereed a certain paper in combinatorics during the break. And this was amazing. I believed the result, and then I found a counterexample because it was intuitively clear that it should be the case. Nonsense. I mean, it was wrong. Okay, so one has to be really, really careful with intuition. Yeah, one should really check it. So I hope I wasn't misled by my intuition here, and the reasoning I'm going to spell out for you is fully complete and rigorous and correct. Okay, but first let's write the lemma, which I announced at the beginning of the lecture. Well, the phrase is very much similar, so restricting morphisms in the category MPIG to the morphism satisfying regularity condition yields a subcategory. Of MPIG. Now, at this point, you should complain of why I'm restricting MPIG instead of restricting the IPG. Is the MPIG? No, sorry, MIPG. Oh, I'm committed. Not bad. Because my first thought was to prove it in IPG. But I got lazy. A, we don't really need it, and B, I don't know how to prove it because I'm using the M condition to prove this lemma. Okay. What I need is the injectivity on edges, which is implied by the M condition, obviously. Okay, so let's go through the proof. as before to begin with. What happened? Clear. Why does it stop writing? It is clear that I don't know why. What's going on? So I have a problem with my pen. Okay, it is clear that the identity satisfies the regularity condition. Ah, yes. Maybe I should just recall the regularity condition. Okay, it is clear that F equal ID satisfies the regularity condition. Okay, let me remind you what it is. Okay, it concerns all regular vertices in a graph. So it must hold for all regular vertices in the source graph E. Okay, and you have two conditions. First is that when you apply homomorphism F to the set of all edges emitted from V, that's a certain set. I denote it by FV, FV. So by the way, I changed the notation. It used to be FPV, but no, this was a wrong notation. I call it now FPFV. Okay, so this set, well, it's a certain set of paths which starts at f of v. This is why I have this f of v. Has to have the following properties. So for any, okay, this is the set of paths. Now, a source in FPFV is a vertex such that it emits. Well, that's not a good name. I don't know, because sources are things that do not receive anything. Yeah, I should change it to emitter. Yes. What's going on now? The internet is stuck. What's? Maybe my battery is going down. Yeah, guys, I'll pause the recording and I have to change the battery because it's definitely the battery in my pen. Pause, where is pause? My mouse, okay. Okay, so an emitter. In FPFV, okay, is a vertex such that it emits an edge belonging to a path that is an element of FPFV. Right, so FPAV is a certain set of paths, okay? And now paths are built out of edges. Edges have their beginnings. And I'm looking at the beginnings of all badges from which I build paths in this set, okay? And I call such guys emitters in FPAV, okay? And the first condition is, so these are two explanations. A is what I mean by FPAV, that's this set. B, what I mean by my emitter. And now the condition. The condition is that each such an emitter maybe like this. No, let me write it. All edges emitted from such emitters belong to paths in FPAV. Okay, so in other words, and this is exactly where the difficulty was, how to grasp this condition and then verify its behavior. I did it in some iterated construction way, and then this was really hard to manage. But I think this is a much better equivalent formulation. So what we are saying is that this set has the following property. It consists only of such paths. When you look at any path in this set, then you look at vertices at which edges of such path begin, and then every other edge that is emitted from, yeah, there's another condition, and then all these guys must be irregular. So maybe B is also a condition, and emitted it is regular by assumption. It is regular. It is a regular vertex. Okay, so all these vertices are regular, and you must have a property that all other edges that are emitted from such emitters also belong to paths in this set. So you have to make up your mind. If you have a vertex, you might hit it with some edge which belongs to your path, but then either you continue with all edges emitted from there or with none. What you must not do is that out of 10 edges emitted from your vertex, you take 5 and the other 5 you ignore. Everything or nothing. Either you invite everybody for the wedding or nobody. So that's the property. Any questions here? That's why it took me so long to prove this lemma. Well, and then condition 2 is just bijectivity condition, okay? By assumption, you know, that FPAV is the image. I want it to be bijective. So simply you assume that it must be injective. Okay, and here this is why I used M condition in my proof, because I need this injectivity of edges. Okay, when the reasoning seems to be very simple and quite accessible. Okay, so that's the regularity. So I told you, I warned you, this is a convoluted and complicated concept. Although that's exactly the concept which worked in proving the functoriality, covariant functoriality of Levitt-Path algebras. And this is an important new concept, I believe, because it goes way beyond not only what you can find in books, but also in recent research papers, at least in our papers. Okay, So to begin with, it is clear that F satisfies the regularity condition. Well, I think here it's no-brainer. It's F is identity. Then FPFV is simply the set of all edges emitted from V. And identity map is typically a bijection. And of course, this construction is satisfied because you map all edges emitted from V to all edges emitted from V, right? So all paths in your set are just edges, okay? And these are all edges that come from that emitter. So that's, of course, is preserved, okay? So that's not a big deal. It's a triviality. Now let's handle this composition condition. Okay, so assume now that we have morphisms in M IPG. Right, I guess before F going from E to F, and G going from F to G are morphisms in MI. Okay. So then by the previous lemma, the composition of G and F is injective on edges. Why? Because you see, M condition obviously implies injectivity on edges, all right? Because equality implies inequality, and inequality implies equality, right? You have this, if I have that F of E is equal to F of E prime, that is implies that F of E is less or equal to F of E prime, and this implies E equals to E prime. So of course, the M condition implies injectivity, okay? But it was not obvious at all that the composition of such things is again, well, the M condition is again satisfied, all right? It's not so easy to argue is, oh, okay, I'm injective on edges, I compose, so two guys injective on edges should become injective on edges. Well, it's not so obvious because when you compose these maps, the second map is applied not to edges, it's applied to paths. So the reason why you can so easily say, oh, IPG forms a subcategory and this is injectivity of vertices, that's because any morphism whatsoever applied to a vertex is a vertex, right? So this subset of zero length paths is closed under any morphism whatsoever in any category of graphs. So here, of course, it is preserved because F of a vertex is a vertex, and then you are injected on vertices at both stages, so you are injective after the composition. But you cannot so easily claim it with edges because here we are not assuming that the composition of the image of an edge is an edge. Okay, so maybe F of one edge is a path, of F of another edge is another path, and then G glues these two paths because it's allowed to glue paths. So that's why we needed this lemma, which we just proved. But now that we proved that the M condition is preserved under the composition, well, we're home and dry because M condition obviously implies injectivity. Okay, so let me erase this side remark. Okay. Is injected on edges. Okay. Okay. So, assuming the regularity of F, we conclude. Well, we infer that the composition GF going from the set of all edges emitted at V to G of FP FV is bijective. Right, because by construction is subjective. So I'm using the regularity of F in order to say that the image of S, pre-image of V under S, under F. So in other words, F of this set is FPFV. That's what regularity tells us. Okay. Otherwise, I would just write some triviality in set theory. But using the regularity of F, I know what is the partial image when I apply F only. And now, well, I have to apply G and see that nothing goes wrong. But I already know that this map is bijective. Well, because it's by construction surjective, because I wrote it as a map onto the image. And we know from the previous lemma that G composition F is injective. Okay. So therefore, it suffices to show that this mysterious set G of FPFV is nothing else but FP of G of F of V, right? So that it satisfies all these axioms. This is a certain set to which edges emitted at V are mapped, and this is a set of paths that are emitted from the edge G of F of V. And this set of paths have to satisfy these weird regularity conditions, okay? So for starters, you have this thing here that every such emitter must be regular. But that's trivial, that's obvious, because the regularity condition implies that regular vertices are mapped into regular vertices. So here nothing goes wrong, okay? All emitters that are in here, right, are regular vertices. So G applied to them gives you regular vertices, and by by the construction of you have that. Well, because what is this map really doing here, right? I take here a path. Path is built out of edges. So in fact, I'm taking an emitter and all edges emitted from this emitter, and I apply G to it, and I replace these edges coming from this vertex by a set FPGW, where W is this vertex, and by construction, this set has all these regularity properties. That's because G is regular. Okay. So regularity very easily falls into place, okay? So let me write it down. So for starters, all emitters in, because, you know, proving this equality is simply checking that this set, which we explicitly construct, has the properties that deserve this name, okay? So for starters, all emitters in G, F, P, F, V are regular. Right, one more time, because what are we doing in order to map path into path? Well, this is a morphism, so I chop my paths into edges, and then I map edges, and then I recompose them after mapping. So basically, what I'm looking at, I'm looking at some vertex W, which is in F. It's a regular vertex, of course, because it's in FPFV. So it has finitely many and non-zero edges. And I map it by G. Where do I map it? Well, I map it to paths which originate at GW. Now these are paths, and they form the set FP GW. Okay, this set is SF, the preimage under SF of W. Okay, so these are all edges emitted at W, and this set is mapped to the set of paths emitted at GW, and that's this set FPGW because G is regular. Okay. So you can see that obviously this vertex is again regular, but by definition by regularity of G, and then each and every vertex which is involved here, I mean emitter, is also regular, again by the construction of FPGW by the definition of G. Okay, and it happens at every level, so you can see that really each and every vertex which is an emitter in this set is regular. Did I get it right? Anybody complains? But in fact, I think that this sentence belongs later on. So no, let me rewrite this. I told you that I finished this lemma 15 minutes before the class. Now let me, because it's kind of pointless to make an argument without explaining the construction. And what I just drew a picture of, I mean, it's also written, right? So what happens is that at each vertex W that is an emitter in FPFV, we replace the preimage under SF of V. So a set of all edges. No, sorry, this is W. So the set of all edges emitted at W, we replace this set by as I was explaining, FPGW. Okay. And now I can write. So first, all emitters. Yeah, because that's how I get this set. I look at every vertex which is involved there. I look at the set of all edges which are emitted there. And of course, they all are parts of paths by definition. And then I replace these edges with paths. So all emitters in P of V and G of this are regular. And do we have a second condition, which I was explaining when explaining the definition of regularity, okay? And all edges and all edges emitted from emitters in G of F, P, F, V are used in paths or belong to paths in this set. That's it. That's exactly this condition. Well, and why is it the case? What kind of vertices you have in this G of F, P, F, V? Well, first you have this G of W vertices, okay? And what happens at G of W that by the very construction of FP GW, you are taking all edges that start at GW, and some of them you prolong to pass, some of them you don't, okay? But you use all of them, right? So you have no problem with vertices, emitting vertices in G of FP of FV, which are the form that they are in the image of G. And now if you take some other guys, which are perhaps not in the image, so they are not, you know, of the form GW, where W comes from FPFV. Well, it's also no problem because they're sort of internal vertices in this construction. They are not these roots, you know, of these replacements. They are not of the form of GW. But even if they are internal, still this is this construction which by the regularity of G says, aha, if I use an edge emitted from this vertex in my path, then all other edges emitted from this vertex are used in my path. So again, this is satisfied. And so it's satisfied for all vertices. So therefore, we end the proof by saying that the equality star holds as desired. As well. And I would call it a day. If there are no other questions, I stop recording and we resume at 4:15 for the recitation class. So see you there. Bye.
Bye.